Good morning, grade 1S students. I hope you are doing well. Today we are going to start a new chapter, Mechanical Waves. This lesson is very interesting. Please pay attention, open your copybooks and write all the notes. Can you imagine our world without radios, televisions, telephones, guitars, loudspeakers, x-rays and internet? All these sources of fun use sound, light, or other waves to stimulate our senses of hearing, seeing, and allow us to communicate with each other. Indeed, all the information that reaches us travel in waveform. Suppose you pluck a string of a guitar. The string vibrates and produces musical sounds in the form of waves. Vibrations are also called oscillations. Vibrations produce waves that propagate in a given medium to reach and stimulate our senses. Vibrations or oscillations are regular to and fro motions of an object between two extreme positions. What do I mean by regular to and fro motions? It is the movement back and forth. Look, for example, in this figure. Here is a vibrating ruler. It vibrates between two extreme positions, A and B. When it vibrates, it produces waves as shown in this figure. Vibrations produce waves that travel away from the source. As they travel, the waves transport energy but not matter. For example, look at this picture. The falling droplets of water are considered signals. They create the waves. So once they disturb the surface of water, circular waves are created that propagate away from the signals. As you can see here, that these circular waves propagate away from the signals, away from the falling droplets. What do we consider here the surface of water? The surface of water is considered the propagation medium because simply waves are being propagated in this medium. What is a mechanical wave? A mechanical wave is a disturbance in matter that transfers energy through the matter. So a wave that can only propagate in a material medium is called a mechanical wave. Some of the most common examples of mechanical waves are water waves, as seen previously, sound waves, and jump rope waves. Look here, the waves created by the rope propagates in the rope. So this type is called mechanical wave. It needs a material medium, which is the rope. However, in the second picture, this schematic representation represents sound waves. We all know that sound waves propagate in air. So the medium, the material medium is air. This type is called mechanical wave. There are two types of mechanical waves, transverse and longitudinal. They differ in how particles of the medium move with respect to the direction of the wave. Suppose here that the direction of the wave is in this direction. If the particle vibrates up and down, it vibrates perpendicular to the direction of the wave. So this kind of wave is called transverse. However, in the second case, if the particle vibrates back and forth, then it vibrates parallel to the direction of the wave. This kind of wave is called longitudinal. So, in a transverse wave, particles of the medium vibrate up and down perpendicular to the direction of the wave. In a longitudinal wave, particles of the medium vibrate back and forth parallel to the direction of the wave. A typical example of longitudinal wave is the sound wave. Let's do a small exercise. So given two figures A and B. In A, compress the string to the maximum, compress it, and then remove your hand. How does the string move? Like this, back and forth. What is then the type of wave? The type of wave is longitudinal because the particles vibrate parallel to the direction of the wave. However, in B, displace the extremity of a string perpendicular to CD. So let's see CD, or the direction of the wave, and let's displace it in a perpendicular way. What is the type of wave? The type of wave is transverse. Explain: because the particles vibrate up and down perpendicular to the direction of the wave. So how do we schematize waves? So for example, this is a wave. The highest point of the wave is called the crest. So this is the crest, crest. However, the lowest point of the wave is called the trough. Do you see here this line? This is the equilibrium line. The equilibrium line is the middle line around which the wave moves. This wave is said to be periodic because its motion is repeated at equal intervals of time. So this wave is continuously repeating itself. This is why I call it periodic wave. What are the characteristics of waves? Waves are characterized by their amplitude, period, frequency, and wavelength. So let's start with amplitude. The symbol of amplitude is A, or it can be represented by x small m, xm. So the amplitude, as you can see in the figure, it is the distance between the crest to the equilibrium line, or it is the distance between the trough to the equilibrium line. This is the amplitude. So since it is distance, so the SI unit of amplitude is meter. Another characteristic of waves is the period, symbolized by T. The period is the time taken for one complete oscillation or for one complete cycle. The time taken for one cycle is T, capital T. Graphically, it is the time between two crests or two troughs or three consecutive points on the equilibrium line. So this is the first point, second point, third point. This is one cycle. The time taken for one cycle is the period. The SI unit of period is seconds. And here we have a relation between T and the period. If one cycle takes period, capital T, n cycles, what is the time taken for n cycles? It's very easy. T equals n times period. Memorize this, please. The third characteristic of wave is the frequency, symbolized by F. Frequency is the number of oscillations in 1 second, or the number of cycles in 1 second. How much does the wave oscillates in 1 second is the frequency. Its SI unit is Hertz, Hz. How can we calculate the frequency if the period is given? Frequency equals 1 over T, so T equals 1 over F. Some important note here. To find the speed of waves, we can use the following formula. Speed, also known as velocity, its symbol is V. V equals the distance traveled by the wave divided by the time taken by this wave. The speed of a wave in a given medium is always constant. Now, if the speed and the time are given, you can find the distance by multiplying speed by time. So distance equals speed times time. The SI unit of distance is meter. The SI unit of time is seconds. So the SI unit of speed is meter per second. The fourth characteristic of wave is wavelength. Its symbol is lambda. This is lambda. Wavelength is the distance between the crests of the wave. This schematic representation shows a wave. These are the two crests, so the distance between them is called the wavelength. It is expressed in meter. However, other units can be used like micrometer, millimeter, nanometer. When given these units, please convert it back into meter. So given the formula, speed equals distance over time. So in case of a wave, the distance between two crests for one cycle is lambda, right? So instead of distance, I can write the lambda, which is the wavelength, and instead of one cycle, or the time for one cycle, is the period. Please review the definition of the period. Period is the time taken for one cycle. So the time for one cycle is period. So V equals lambda over T. Speed equals the wavelength divided by period. But frequency equals 1 over T. So instead of T, we can write frequency. So this formula can be also written as lambda times 1 divided by period. This is the same as this. So instead of 1 over period, I can write F. So speed equals lambda times F. Speed equals wavelength times frequency. The first example, if the speed of sound is about 340 meters per second and the frequency of the wave crest is 20 cycles per second, find the wavelength of the sound waves. So first, write the given. So given that the speed equals 340 meters per second. So wave velocity, or the speed, equals 340 meters per second. And given that the frequency is 20 cycles per second, so you write 20 cycles per second or 20 hertz, the same. Find the wavelength. So let's apply the formula. From the previous slide, the wavelength equals velocity divided by frequency. So lambda equal, substitute, instead of velocity, write 340 meters per second divided by 20 cycles per second. So lambda, you remove second with seconds, so the remaining is meter. So lambda equals 17 meters. So the distance between two crests is 17 meters. So the wavelength of the sound wave is 17 meters. Now please pause this video, copy these two exercises on your copybook and try to solve them as a homework. Thank you and see you.